I'm a computer scientist, we didn't have a number. We didn't have a measure for wellness. And that's actually what introduced me to the aging space and got me interested in bioaging. Actually, Morgan Levine's 2012 paper on bioaging really struck me as like, wow, aging is sort of this meta disease, which we can use to quantify wellness. And so as a result of that, I should also disclose, I actually created the BioAge product based off of the research that I'm going to present today that is currently sold at Thorne. But I wrote a paper and we created a BioAge from about 3,558 individuals in the Aravel program. We had 2,000 women, 1,400 males. We had a nice distribution of age. We actually had a lot of longitudinal observations. And I created this BioAge using the genomics, proteomics, metabolomics, and clinical labs. And the main findings of this paper were that the biological age estimate was variable under different omics. We saw that it rose under disease conditions. And we saw that participation in a lifestyle program actually improved their bioage. We also saw that the plasticity was affected by sex. We also saw that current health status affected how much you could change your bioage. We also saw that the blood factors, when you grouped them together, we saw themes in metabolic health, inflammation, and bioaccumulation of toxins. Now, we estimated bioage using the Comera-Duval algorithm with a PCA transform. I think I've heard some people talk about this. This was what Morgan did in 2012. We found that it had the best slope for 1 to 1 year without much regression to the mean effects on the tails, which you sometimes see with penalized regressions. We included principal components from the genetics to sort of account for ethnicity, race, those sorts of things. We used clinical labs. We had both LabCorp and Quest. Think really good clinical panels, like you got a really thorough checkup. Then we also had O-link proteins and untargeted metabolomics from Metabolon. And this is the plot of the estimates from the joint biological age. We also separated them out and did them independently. We saw that the proteins had the lowest root mean square error. And feel free to take pictures, but I'd prefer you read the paper. They're all in there. These are all figures from the paper, please. But the proteins were the most accurate. The metabolomics were in the middle, and the clinical labs had the highest variance, is what we saw. But keep in mind, as you should all know, accuracy is not the goal. A perfect predictor of chronological age is, your birthday. So, and also, I think with the clinical labs, a lot of what I saw in there is that, these people all had good health care. And, when, they'd be taking drugs. And so a lot of these markers didn't track necessarily with age because they were under treatment. And I think that might explain why some of the proteome and the metabolome seem to do better. Now, we also compared these to each other. So we took the delta age, and we checked to see how well do they correlate with one another. Are we getting the same signal? Is there a latent vector of wellness in this aside from the noise? And we saw about a 0.25 correlation between each of the different omics. So they do agree with each other better than they agree with chronological age, but they definitely each contain their own unique information. Now, another question, if you want a wellness marker, does this reflect the things that we think of as wellness? And so these are the disease conditions that these people came in with. And as you can see, in every case where there is a significant positive, there's a significant correlation, that effect is positive. And I think some of the things that had the most effect you're going to expect. I don't think anyone who does bioage is going to be surprised to see type 2 diabetes has a huge effect on bioage. Now, another fun thing, this wasn't actually in the paper. This is in my dissertation, which is available at the University of Washington. This was kind of preliminary data, but I did bioage on some cancer patients, women undergoing cancer therapy, I think at the Hutch in Seattle. And we had some breast cancer patients, and we had some ovarian cancer patients. And I find this very interesting. In metabolomics, the breast and the ovarian cancer patients both had much higher bioages. And the ovarian much worse. If you know cancer, breast cancer, there's a good chance you're going to make it. Ovarian cancer usually comes in at stage 3 or 4. These are very sick women, unfortunately. But you can see that that's reflected in their bioage. also interestingly, well, we didn't see that much proteomic signal in the women who were undergoing breast cancer therapy, whereas the ones that were undergoing had ovarian cancer were very sick. And so this says, of course, women undergoing cancer therapy are not well. And so as you can see here, I just love that. That never got really published, just in my dissertation. Project got canceled. But in any case, participation in a wellness program. So this is lifestyle interventions, nutrition, exercise. Those they were being coached by a nutritionist that was trained in behavioral health modifications. So what we saw overall, participation in a wellness program decreased the slope of bioage, basically a 1-year decrease. We saw that women responded better to the treatment at a 1.5-year decrease. In men, it was about a 0.8. We also saw that if you came in really healthy, so if you were a health optimizer, your nutrition was already dialed in, and you came in with a low bioage, that the slope remained around 1 of your age for the people that we had longitudinal data for. Now, on the other hand, if you came in and you were in really bad shape, your nutrition wasn't good, you weren't doing the right things, we were able to see a big effect in your bioage down to like 1.5 years. So what this says is that bioage is not infinitely malleable, which kind of maps to what you expect. You can't like bring somebody back to infancy. So there is a limit to what at least lifestyle can do for aging. Now we saw these different themes of aging. As I said, metabolic health. One of the nice things about Comare-Duval is that you can estimate the effect sizes. You do a little math, and you can basically get back the coefficients. And we saw that there was a strong signal for metabolic health. Higher glucose makes you older. Higher HbA1c makes you older. A Agouti-related peptide makes you younger. BDNF was on there too. But we also saw inflammation markers where a strong lymphocyte count made you look younger. And monocytes, on the other hand, if your innate immune system is up, then it made you look older. And then another theme that we saw, especially in the clinical labs and the metabolites, were bioaccumulation of toxins. So we see, lead goes up over time, mercury goes up over time, the forever chemicals, the PFOAs, PFOS, they go up over time. And you can see these same trends in the metabolomics and the proteomics. And I have the coefficients for everything in the paper. Please read it. In any case, as I said, the biological age estimate was variable under different omics measures. It rises under disease conditions, and that you can change it. You can change it through lifestyle modification. Now, the plasticity is affected by age and current health status. And generally, we saw 3 different themes, which I believe Mike Snyder found pretty much the same ones, except he didn't see toxins and instead had liver and kidney. But metabolic health and inflammation are obviously 2 very important themes within bioage. As I said, I made a thing. You can buy said thing. And I wanted to talk a little bit about what the Price Lab is up to now. As I said, we went into industry in order to make a thing. We made some other things while we were there. And then right now what we're working on is we started a new lab at the Buck Institute just 3 months ago. And we're working on building what we're calling the N of 1 analyzer and the N of 1 interpreter. And what we're interested in is taking these deep multi-omic data sets, identifying abnormal values using machine learning on a personalized N of 1 basis, then using systems biology, mapping things into networks, using mechanistic information about how these analytes work together, and machine learning to identify perturbations within our systems. And then we're very excited to be applying LLMs to knowledge graphs in order to develop context over the markers that we are looking at. So when we see something out of range in a person, we can identify when these 2 things are related using semantic reasoning. And building a big corpus over an individual's personalized health profile, and then taking that corpus and trying to develop actionable ways of improving one's health and identifying early disease transitions using this data. And so that's what we're working on now. And we got a couple people working on it. Considering we were 2 people about a month ago, we're growing really fast. And we're really interested in finding smart researchers here, postdocs that are interested in this sort of work and growing the lab further and kind of making this a reality. So thank you very much.
So much, John. Thank you also for sticking perfectly to time. So unfortunately, we're still a bit behind, so there won't be any questions now, but please do find John. And thanks again so much. So next up, we